Right then, question 9 here is talking about the energy of a orbiting satellite. This is where we're dealing with a non-radial, a radial field rather than a uniform field. So we're talking about the more complex side of gravitation. We have to use expressions that are given in the data booklet to help us get where we need to get to. First question here is dealing with a shuttle of mass m that is launched in the direction of the Earth's south pole. I won't worry about that but too much, but it's been given a particular amount of kinetic energy which we call EK. It's been given that much kinetic energy. What they first want you to do is, given these details about the Earth, m of the Earth, the radius of the Earth is RE, they want you to show that given EK of 7 GMM over 8 RE, that it will not be able to escape completely the Earth's gravitational field. So what we need to use there is the idea that we know what the kinetic energy has got to exceed. Well, if it needs to get to exceed this, it would have to escape completely the amount of potential energy that would be given to something to get to infinity. So the EP at the surface of the Earth is a very negative number. It's given in the data booklet, it's minus GMM over RE. If you want to take something and escape completely the Earth's surface, you would have to exceed that amount of energy in the kinetic form. So our kinetic energy, EK or KE, needs to be greater than the potential energy, which is very negative, at the surface of the Earth. Remember that the potential energy reaches zero at infinity, and that's where we've got to get this satellite to. Well, how much energy have we been given? We've been given a kinetic energy of 7/8 GMM over RE. Well, that's clearly less than the potential energy at the surface. The requirement to get it to infinity is GMM over RE, so it wouldn't quite make it. Our other possibility of doing this is to actually look at the velocities, the escape velocity required and the actual velocity at the surface of the Earth given that kinetic energy. So you can quote V escape, which is given in the data booklet. It's given as root 2 GM over RE, and then you can develop from the kinetic energy given, and that's our kinetic energy given, what velocity is that equivalent to? Well, just make a half mv squared equal to that amount of kinetic energy. Energy is energy, and you can quickly derive that you're left with this is our velocity that energy would give. Root 7 gm over 4 re, which is clearly less than the root 2 gm over re by a little tiny bit. Question 9 continued, part B, part 1. This one now, the satellite has been put into an orbit of radius r around the Earth, and we're now going to analyse the different energies that are going on with this satellite in orbit. And we've got three energies that we can look at. We can look at the total energy, we can look at the potential energy, and we can look at the kinetic energy of it. So the total energy, as you think in energy terms, is going to be equal to, so that's our total energy, that's going to be equal to your potential energy plus your kinetic energy in an orbit. Now we already know that potential energy in previous parts and also in our data book, our potential energy in a radial field is given as minus GMM over R. You've got to derive a value for EK, because if we know the potential energy and we know the kinetic energy, we can then actually derive fully a value for ET in terms of potential and kinetic energy. So how do you derive EK in this weird form? Well, what we do is we take our minds back to centripetal force, which is mv squared over r, and gravitational force, which is GMM over r squared. For an orbiting object, those two will be equal to each other, equivalent to each other. So what we now need to do, I'll take those bits out of the way. I'll just delve in a little bit. We've got mv squared over r on the left-hand side, GMM over r squared on the right-hand side. Well, how do we get kinetic energy out of that? Well, what we've got to do is get rid of the r on this side, so multiply up here. That gets rid of that r and that r over there, and then divide both sides by 2, and that means on the left hand side now, that is a half mv squared. That's kinetic energy, and that equals gmm all over 2r, which is this thing here which I've shown there. So that's the derivation of ek. So now we can slip our two values of EP and ek into our existing expression up here. Let's put them in. So here's our potential energy, here's our derived kinetic energy. That's minus gmm over r, a whole one value of that. This is plus a half gmm over r, giving us a total of minus a half gmm over 2r for our total energy. Therefore, I have shown that derivation. Right, part 2. It says using the expression for ek in part A, so that derived expression that we got here. Then I want you to determine a general value of the radius in terms of RE. This is quite a tricky question. The way of doing it is to think of energy equaling energy. So I've gone for the total energy at the launch here. That must be equal to the total energy that you got in the orbit. So we already know the total energy in the orbit. We just derived that expression there. So slip that in here. That's our total energy in the orbit. What are the total energies at the launch? Well, partly it's potential energy because of position, and it's also then going to be the kinetic energy that's given at the launch as well. So here's our potential energy being at the surface of the Earth, radial, so it's minus gmm over re, and then I add our kinetic energy applied at launch, at the launch pad, 7/8 gmm over re. Now after a lot of cancelling out, you can get rid of, you can just cancel out the constants here, and if you do that, you're left with this expression here and a little bit of fiddling around. It's not too difficult to hope. You find that 1 over 8 re equals 1 over 2r. Cross multiply that, you find that r is generally equal to 4re. Very nice question. Finally, we have this one here where I've drawn an extra little graph down below which you might find familiar. This is the one that shows how in an orbit ek, et, total energy, and ep vary. This should be energy here, and this is radius here. So how do those three energies change for an orbiting object? Well, they change in this way, and this is something you do need to remember, and each one of those curves follows the derivations and the various ones that are given in the data booklet as well. I'm going to use that in this final question. It's asking you to talk about what goes on if a shuttle, for instance, starts colliding with air molecules in the upper atmosphere. What would actually happen? I think it's quite intuitive that you'd know that the shuttle would reduce in terms of its radius. It's a typical thing that would happen. It's one way of actually getting a satellite out of a high orbit is to take energy away from the orbit itself. So you've got to reduce the total energy. And it actually says here, look, the total energy of the shuttle decreases as it collides with air molecules. So the total energy does decrease. So if that happens, and if we now look on this graph, here's ET, this is this curve here. If the energy decreases, becomes more negative, and I'm taking it more negative by going down here, follow that line. Let's say we start here. If I go down here, my total energy is decreased. It's become more negative. What's happened to the radius? Well, it's reached that point. The radius has decreased from that point to this point here now. So the radius decreases. Now, as r decreases, so look, follow it decreasing like that, what happens to the kinetic energy? Well, we pick the same starting radius and decrease the radius. Oh, look at that. The kinetic energy is increasing. So as r decreases, the kinetic energy increases. Kinetic energy is motion, so the speed increases. Wonderful question.